In logic, we are used to the idea of building up formulas using connectives such as AND and OR. In this talk, we explore how we may be able to deal with connectives which cannot necessarily be expressed in terms of AND and OR operators, and these more general connectives are better expressed in terms of graphs. So we move beyond formulas and look at building proof systems or logics on general graphical structures. This is joint work with Matteo Acclavio and Lutz Straßburger. I am Ross Horne speaking. We begin with an overview of the talk. We firstly want to motivate why we would want these additional structures. Why would we want to do logic on graphs? And in short, it's because we can end up with structures such as the following. See this N shape here, which cannot be constructed in terms of AND and OR operators. And we can find a context in which they are useful. We then think about, well, if there has been no logic designed for such structures previously, in the sense that we mean, then how do we go about designing this logic? So we want to build the logic from logical principles. For instance, we would want to have that if we have some graph here, that the graph should imply itself. This is something which would be very worrying if we did not have in a logic. So we start with very simple assumptions like this and essentially build a system. And then we go on to examine some of the challenges that we face. And a really important thing is that we needed to go beyond the standard proof theoretic toolkit that we use from day to day. So for instance, if we have a structure like this, so we have the atomic proposition A, and we have some graph which is in a disjunction with it, we should be able to rewrite that graph to become the complement of that atomic proposition, and thereby apply a rule to that atomic proposition. This is a standard result. And notice that here in this formulation, we have some additional information here. We have some additional context. We need to do things inside context, be much more context aware than we have previously. Of course, this context is provable, and we'll see this pattern arising later in this talk. This work stems from some rather simple observations in ubiquitous structures, such as queues. And queues are used, of course, in distributed systems for reliability, for instance, ensuring that a series of messages arrive in the same order in which they were sent. And if we want to model a queue, graphically, maybe we want to do it like this. So we could enqueue something. So A is just something that we're putting in the queue. And if the queue was allowed only one thing to be in, it's a very short queue, then we would have to dequeue A before B can be enqueued. So B cannot be enqueued before A is dequeued. And we can represent such one buffer as a formula using a non-commutative binary connective as follows. Similarly, if we want to model a 2Q, what we can do is we can enqueue A, we can enqueue B, but if we want to enqueue C, firstly we must enqueue or dequeue A, because only two things are allowed in this still rather short queue. And of course, we can model this as formulas, but this is getting a little bit more complex. Let us break this down. What's happening here? Well, we have the enqueue A event. Now, everything happens after this enqueue A event. So we have a binary operator here. And what happens here? Well, we have everything before the box, i.e. the enqueue A event, is related to everything inside the box in the same way. And similarly, everything after these two enqueue and dequeue events, everything is related in the same way. So we can actually break this down into another operator, and we can actually say, well, these are two things in parallel. So we can decompose a 2Q using series and parallel operators, using binary operators. The surprise is that if we want to do the same for a simple structure such as a 3 buffer, this is just a queue in which 3 things can simultaneously be queued, we cannot write down a formula in the same way, nor can we do it if we have, for instance, unbounded buffers. And the reason is has been known since the 1970s. In short, it's because whenever we have this N-shaped structure appearing as an induced subgraph, so this appears all over the place in these structures, these N shapes, then we cannot write down a formula in terms of binary operators to represent this pattern of dependencies. We were looking at asymmetric dependencies. We have these non-commutative operators, but the same problem even arises for much simpler structures, the more and or-like structures. For instance, here we have that A is separated from B and C is separated from D. So we're looking at the symmetric operation of separation. And what this represents is because A and B are separated, they cannot communicate, but B can still communicate with C and can communicate with D. And we can represent this, of course, as a formula. So we have the A tensor B here, and we have the C tensor D, or AND. Tensor is and we have the OR here, which is this power operator. Why we're using linear logic style notation will become clear later. And of course, we could represent this structure. So what's happening here? B can communicate with C, but B can communicate with D, but B and D could not communicate with A or C. And of course, we can represent this pattern of dependencies using binary operators. But look at this. We cannot represent it. Again, we have this N shape appearing. This is in fact the P4 graph, the path on 4 vertexes. And this N shape cannot be represented using binary operators. And it may be a real life problem. So for instance, we have some angry person who's trying to communicate with either the technical support or the manager of the company. He's happy to talk to either. But the CAM person doesn't really want to talk to the manager. He just wants to talk to the technical support, doesn't want to get involved there. The manager doesn't want to get involved with the technical support either, because he's above these kind of things. So we have policies which are separating people, but we're still allowed some communications to happen. And this simple network could not be represented if we built things up using binary operators representing separation and concurrency, as illustrated previously. So we can only model separation really in networks of diameter 2 because of this restriction that we cannot have paths of length 3 appearing in our graphs which are induced by our formulas. How do we even go about designing such a logic, given that we have no semantics or reference points for logics and such a systems? Well, we could start, for instance, by looking at cographs, which are the graphs generated by formulas. So, for instance, we would want to forbid the following inference, probably, where we have this bow tie appearing out of nowhere. And this corresponds to forbidding an inference such as the following, which is expected in pretty much any logic. So if we didn't forbid this inference, then and OR would collapse. We might also want to permit the following inference. So what's happening here is a little bit more complex. Essentially, we have this disjunction of 2 graphs, and the graph on the right is moving inside the other graph. It's moving inside a module, or a module of a graph is essentially a subgraph which is connected to everything on the outside in the same way and works like a context in formulae. And you can see that the module is grown above and the graph on the right has moved inside the module. Essentially, this corresponds to a rule like this, where you can see the formula on the right has moved inside another formula, and this is admissible in pretty much any logic you can think of. So we have some reference points that things we don't want to violate. But how do we consider the inferences which are allowed or the rules that were allowed when we have graphs which don't correspond to formula, such as this N shape that we see there. Okay, we weren't allowed to have the bow tie appearing at the top, but should we allow, for instance, an N or disallow this? What about if we can be moved from a V shape to an N shape? Should this be permitted? What about the third structure here? We have an N and its complement. And what's happened above is every dependency has been added except the dependency which is basically allowing the A and the not A to appear in the same context as each other. So there's no dependencies between A and not A. Similar between B and not B, C and not C, and D not D. So which of these should we allow and which ones should we forbid? The first problem we face when designing logics on graphs rather than trees is that we have no longer subformulas. But we can recover this by using the concept of a module, which I mentioned previously. So a module is essentially a subgraph, such that everything inside is related to everything outside in the same way. And we're going to use context-like notation as we would for formulas to denote a graph which contains a module M. Okay, so modules generalize subformulas. Another concept we're going to require is the concept of a prime graph. And a prime graph is essentially a graph which contains no non-trivial modules. So it can't be decomposed any further. And these four graphs in front of you are examples of prime graphs. We're going to use a bit of a notation here. Notation, this kind of bracket that we're going to use will denote an operator which is essentially one of these prime graphs, say P is perhaps the N shape, where a number of graphs, say A1 to AN, replace each of the nodes inside the graph. So this is our n-ary connectives formed from prime graphs, or graphs in general, in fact. And if we take cographs, which are those generated by formulas, of course we can decompose them. If it's a non-empty cograph, then it can be a singleton graph, just an atomic proposition, or it could be a disjunction, or it could be a conjunction. But in graphs in general, there's a third possibility. It could also be a prime graph formed from one of these operators. So we can recover the tree structure using these modular decompositions of graphs. Bear in mind these definitions. We come back to the question of designing the logic, and for this we look at some universal logical principles, or not quite universal, because not every logic necessarily has an involutive negation. But we design our logic such that it does have an involutive negation, which gives rise to De Morgan dualities, of course. And we also require consistency, which is that if G is provable, then the complement of it is not provable. And essentially, if we make these two assumptions already, we can say that negation must be defined as graph complement. There's no other choice that will satisfy these conditions. And graph complement gives rise immediately to the De Morgan dualities that I mentioned. So this is here we're using this generalized connectives for any graph, and this means the complementary graph or the complementary connective, much like and or are related. Indeed, those are both prime graphs. And already we can exclude some theorems just from these two principles. We can say, for instance, the following cannot be proven, since the complement of this graph is, of course, A naught related to A, related to A, related to A naught, which is exactly isomorphic to the graph itself, and therefore consistency could not hold if it were provable. We also add some other logical principles, which are again are fairly common, but not absolutely universal. For instance, in intuitionistic logic, you do not have implication defined as not something or something else. But in several logics, such as classical logic and linear logic, it's quite a normal thing. So we're going to require that negation is defined in terms of disjunction and negation as represented here. Okay, we're going to require that implication is reflexive. This is a very reasonable assumption indeed. And we're going to assume transitivity. If you can imply F implies G and G implies H, then F implies H. This is a fairly common principle that it would be pretty worrying if you didn't have in a logic. The next one is maybe not completely universal. I think people could maybe devise logics where this does not hold, but we want to require that if G implies H here, then G implies H in any context. And remember, contexts are of course built in terms of modules. So this we want to retain in our logic. I'm going to call this distributivity, although it could be given several other names, such as monotonicity in lattice theory. But monotonicity is, of course, already reserved as a word in logic. So, with some effort, if I just give you the principles I've laid out so far, we can already prove everything, all theorems that we would like to have in our logic. But we want to do better than this. We are structural proof theorists, and we want to design a system that is analytic. So analyticity is what Gensen's systems originally had. And basically it means that every conclusion corresponds to finitely many premises. So proof search is, your proof search tree is finite. Of course, it was formulated in terms of subformulas, but already we are in a controversial world when it comes to subformulas, so this is a sufficient definition of analyticity. And also we might as well have that it's Cook-Reckhow, i.e. every rule can be checked in polynomial time. Now, using the rules distributivity, transitivity, and reflexivity, it's possible to generate rules such as the following rule here. And this rule is not as strange as it looks immediately, but what we're saying is that if G is provable and if the context in which G we plug is also provable, then D with a G plugged back into that context is indeed provable. So the parts are provable, then the whole is provable. This is the context on the outside there we can always add due to distributivity, by the way. And this we call the super switch up rule, because it's actually a generalization of the switch rule which applies in logic. We also have from reflexivity and distributivity we could generate the following rule. This is just that not G or G holds, as you get in classical logic and linear logic. So this is not a big surprise here. Again, the context is coming from the distributivity rule. We're allowed to add that. And of course, using reflexivity, transitivity, and distributivity again, we can also generate the duals of these rules, where we swap the premise and the conclusion, we dualize everything. So we get the super switch down rule and the interaction up rule, which actually is a generalization of the cut rule in what are called deep inference formulations. So we will see why we need deep inference in a minute. But this is not quite enough by itself, the set of rules. There was a nice candidate. It seems to generalize multiplicative linear logic nicely to graphs. But there's something missing. So for example, what happens if we want to prove that a prime graph implies itself? So we have n implies n. How are we going to do this? Well, what we do is, of course, we're going to have to dualize one of the n shapes. So this is the dualization of the n. And we have to still be able to prove this implication, otherwise P implies P doesn't hold, which would be weird. And so what we have is a special rule which brings together the components of a prime graph and its complement. And then after that, of course, the A and not A are together and they cancel each other out. So we require, in general, a special rule for prime graphs. This was a key insight that we needed. So you have a prime connective and its dual connective, which is also a prime graph. And then we have all the components. So the first component of the first prime graph will be brought together with the first component of its dual graph, and then everything else, all of these components are in the tensor with related to each other. And of course, using distributivity, transitivity, and reflexivity, we can also generate the dual rule as we did before. So we have this P up rule or prime up rule. And then now we have this rule, interaction and the cut rule can be made atomic, so we can bring them down so they only apply to atomic propositions, and that's by using this these super switch and prime rules. And from this we get our system. Our system, GS, consists of the following rules. It's the super switch down rule, the P down rule, and atomic interaction rule. And the dual rules to these are all admissible in the system. And the interesting thing is that these rules together, they basically, from them we can derive the cut rule. So if these rules were admissible, that is, we can prove all the same theorems using just the system GS as just system GS with any of these rules added, then we have a cut elimination result. And this is the main result of our paper, is that indeed cut elimination does hold for the system GS, this graphical system. And indeed, GS satisfies all the criteria that we laid out, the reflexivity, transitivity, distributivity, consistency, it's analytic, it's Kukurekau. It has all the conditions that we demanded earlier. Most of these logical principles are established via cut elimination, and the boiler room of cut elimination for us is splitting. The splitting technique, what it does is it simulates the rules of the sequent calculus when we don't actually have rules available to us or formulas available to us. Now the idea with splitting is what we can do is we can take any of these connected components in the conclusion of the graph, such as this 7 here, and we could rewrite the rest of the graph such that a rule can be applied to the shape that we've selected, or the component we've selected. And what's happened here is the D naught has moved inside the N shape and then has cancelled out the D. And we're left with two separate components, one which can move to one side of the 7 and one which can move to the other side of the 7. And then we proceed because they're now formula-like, these graphs. Okay. We could also have taken the N shape and then we can renormalize the proof. This is what splitting says. We can take any of these components and we could renormalize, and what happens instead is the not D moves inside the 7, forming a Z shape. And of course we've seen the structure before and we know how to prove it. So this is the idea with splitting. But splitting is a little bit more complicated than it has been previously. So the problem is that if we select the component A now, so this is of a slightly different example. So we select A, and we should be able to rewrite the rest of the graph such we can apply the interaction rule to not A. But we can't do this, so the B out the end prevents this from happening. But what we can do instead is we can treat the rest of the graph as a kind of context, and we can move A inside the graph, and of course we can apply a rule. So we need an additional context awareness to handle these solutions, these particular scenarios. This is not required when we have formulas. This is a particular problem to when we have graphs which allow subgraphs which are P4, with these paths of at length 3. We briefly illustrate another problem which is unique to this graphical system, has not been witnessed before in logics with formulas, is if you look at this scenario here, we have this N shape, and according to what I said before, with splitting I should be able to rewrite the rest of the graph such that it becomes a Z-like shape, even it has some of them are empty components, and then I can apply this P down rule. I cannot do this in this scenario. So we need a special case which is going to allow for prime graphs to be destroyed, and that's what's happening here. So the B naught here is moving inside the N shape and it's destroying part of the graph. And then it's we continue as if with the remaining components that are left. So we allow for the destruction of prime graphs. And this leads us to our statement of splitting, which remember is our core thing for allowing us to do proof theory is that we have the statement, this is a normal splitting result. I mentioned it at the beginning, and there's mentioned that there's context awareness. This was illustrated by an example previously. And we have this case which says, if you have some graph next to some prime graph, then I should be able to rewrite the rest of the graph such that it's a complementary prime graph, and each of these components, k1 to kn, is provable. And of course, there's this extra context awareness which we had for the atoms. And we can do this for every prime graph, but there's a special cases saying that what we could also possibly do is we could break up the graph into two components inside a context again, where one of the components destroys one of the components, mi, inside the prime graph. While one of the main challenges is the proof of splitting, there are also challenges when we apply splitting for showing the admissibility of certain rules, particularly the up rule for prime graphs, and this is one of the cases involved. Details can be read in your own time, so let us conclude. The problem that we have addressed is we have designed a minimal logic on graphs with an involutive negation and the implication defined as not G or H, so as G implies H, and it satisfies logical principles expected of an analytic propositional proof system. These are the rules. There are exactly 3 rules in our system. And our insight is that the deep inference was required, essentially this context awareness and these splitting results. So we've actually generalized further the calculus of structures, which is the basis of deep inference, in order to establish cut elimination here. From cut elimination, we obtain the following results about our system. Firstly, provability in GS is NP complete. We didn't mention this previously. GS is a conservative extension of multiplicative linear logic with mix. It extends an existing, established, well-known logic. GS is consistent, and implication is indeed transitive and distributive. These are our key results.